The stripes going to select quite a lot. It's about to go to any different.
She's like, I don't have to try hard. It's like 10, 15 minutes of my time, this guy to grab me. Like, yeah. Like, I have some birds like that. I had a friend that was checking across the net. And like, you got caught one net, and then like 100 meters down that way, you got caught in another net. And then when we got caught in the third net, we just called it a day. We're like, this guy needs a break.
Yeah, I know. His isn't even baited.
No, it wasn't. He just had to report that.
That poor guy.
The second time, we're like, guys, come on. Third time, we're like, okay, bud, we're sorry. This is our time.
All right. Good weekend?
Yeah, good weekend.
Very well. It was fun.
What about you?
Not too bad. Did your graduate students succeeded in finding some specimens? Right, this weekend? Yeah, I also heard that it wasn't you.
No, not me. Who did?
His girlfriend.
Oh, she found all your specimens.
Yeah,
she found the ones we were looking for.
So don't like give him too much credit for actually getting out there.
You should have told her, like, listen, baby.
He's just like, I found one. I was like, what does it look like? She's like, it's different. I'm like,
You know,
it works.
yes. The one time my wife, my then his fiance, went out and collected with me. She stayed on the shore, and then I accidentally hit her with a jar, I tossed it to her there, and she wasn't paying attention and popped her on the head. I mean, it's a hard plastic jar. Yeah, she never went back out. All right, so we finished up with this fitting distributions, right? QQ plots, Shapiro-Wilk test. All right, definitely prefer to do QQ plots. And we looked at them, and we saw, one that was non-normal, one that was definitely non-normal, but it was probably not so bad that we can't work with it if other assumptions are met. All right, what we're moving on to now is test of location. All right, so generally we're interested in if our sample mean is relative to, there is equal to some known value. All right, so we go out, we know what our target is, that average number of offspring, let's say, is 5. Right? And then we go out and we sample all these nests, and we get a range from 3 all the way up to 8 with an average of 6. So is our sample average actually equal to an average of 5? Well, numerically they're not the same, but we know that that mean of 6 just representing a sample. If we go out and redo a sample, we could easily get a mean of 4. We could easily get a mean of 5, and so forth. So what we want to do is have some way to account for all of that variation, for all that stochasticity in collecting our sample. This is where statistical tests are coming into play. So what we're going to do with these tests is assume that our sample comes from the population of interest. If our sample actually is a random sample from the population, then our sample mean will equal the population. All right, that's our null hypothesis. We're going to test that. Then our alternate is going to be that they're not equal, or that our sample mean is larger than that given value, or our sample mean is less than some value. All right, so we could do either two-tailed test or one-tailed test. Two-tailed test if it's not equal. So we're going to allow our sample to be larger and smaller, or smaller. Or we could do a one-tailed test where we specify direction. All right. So with these tests, by making these assumptions, we actually have an observation. We have our actual sample average compared to our given value, or our proposed hypothesized value. And what we're doing with the statistics is trying to figure out what's the probability of actually getting our value, a value as extreme or more extreme than our value, if this null hypothesis is actually true. What's the possibility? Just random chance would give us our value or something more extreme. So, you know, in the case of offspring, what's the chance that we could actually get 6 or more, or even 4 or less offspring, you know, average offspring size, if our actual average should have been 5? So our options to try to answer those questions are either classical tests or some sort of randomization test. All right, there are some non-parametric tests that we will go over. All right, but our classical test to answer this question is either a z-test or a t-test. That's what we have to work with. All right, if these are unfamiliar and you've never done anything like this, I will strongly urge you to go back and look at all the PowerPoints and homework assignments from the undergraduate course. Those PowerPoints are listed on Blackboard. You can also find the playlist on YouTube where you can go back and watch that background information. All right. If for some reason we violated an assumption, then our option that I'm going to recommend is a randomization test. And with the randomization test, we've got 2 different things. We can do a bootstrap t-test, or we can do a bootstrap 95% confidence interval. Now, bootstrap t-test is a little bit more involved because we have to do some stuff to our data to ensure that our null hypothesis is actually true. All right. So there's a little bit more you have to do in order to actually perform the test. The results of the test, though, match what we get for a bootstrap 95 confidence interval. Since we already have that bs.mean function, the recommendation is just go ahead and do this, because you'll come up with the same answer. You'll come up with the same conclusion. All right. You might not have a p-value, but you'll get the same conclusion. So, z-test. Question with this test is, does our value, our one value, come from a specific population? So we know our population, we know our mean, we know the standard deviation of the population, and then we find a single sample and we say, did this sample come from our population, yes or no? All right. Our hypothesis, or our hypotheses, or null is that it is, our x value is equal to the mean, mu. Our alternate is that it's not, or again, it could be greater or less than, and so forth. How we approach this is to generate a test statistic. And that test statistic, when we do this transformation, is going to be a z. All right. When we do this test statistic, when we take our value, subtract it from our hypothesized population mean divided by population standard deviation over the square of our sample size, that gives a z, which is approximately normally distributed with a mean of 0 and a standard deviation of 1. Now the catch here is that we have one single value, 1 point. All right, and that 1 point means that our sample size is 1. So what we do is we take our x minus mu divided by the standard deviation to get our z. And what that is doing is basically shifting everything so that we are centered on 0, 1. Why would we do this? We would do this if we are using statistical tables to calculate the p-value. In R, we don't have to do it because R will do it for us. All right, so how do we approach this z-test? Actually, so this is our distribution. That's our 0. That's our normal distribution. All right, our x. We do our transformation, and perhaps our z that we calculate is this, is right here. Our p-value represents this area of the curve. So it's a probability that we get a value that's equal to or greater than z. If we do a two-tailed test, we also need this side. All right, so our p-value then represents the area under both of those curves. So what we would do in R is to generate the p-value directly using the p-norm function. All right, so p-norm, we give it our value, what we actually observed at one value point. Our mean is whatever that hypothesized mean is from that population, that standard deviation is the population standard deviation. It's actually the standard error, but it's the standard deviation divided by the square root of 1, which is the standard deviation. And then we specify lower dot tail. Lower dot tail is basically saying, are we down below 0, or are we less than the mean? In which case it's yes. Or is our value greater than that mu? In which case it's false. So we're trying to figure out what area of the curve are we calculating. If we screw up, so if we're looking for this area and we say lower dot tail equals t, we're going to get this big area. And we'll know pretty quickly that something went wrong when we calculate our p-value. We should. We multiply that area by 2 if we are doing a two-tailed test. Alright, and we'll get a chance to do this. So the z-test, we have single value. We're comparing it to a known population. So we know the population mu and sigma. Population sigma. Most of the time, though, we don't know what the population is. We only know the hypothesized mean. So what we have to do then is utilize our own sample to generate that population sigma. In which case, we're going to calculate the standard error, and that changes things. That changes things. All right? How does it change? Well, now when we do our transformation, notice that it's no longer sigma. We're actually dividing by s, our sample standard deviation, divided by the square root of our sample size. This transformation is no longer a z. It no longer follows a normal distribution centered at 0 with a standard deviation of 1. Instead, it follows a t distribution. And a t distribution is defined by the degrees of freedom. So for this, our degrees of freedom would be our sample size minus 1. This n minus 1. All right, this is a t-test. It answers the same types of questions. Is x part of our population? Is our sample x part of our population? Or is the sample mean equal to mu? All right, both of those question types have the same null hypothesis, which is our sample mean is equal to mu. We utilize this t statistic to calculate our p-values in much the same way. We have a t distribution. We calculate our observed t statistic. And then our p-value represents the likelihood that we get data as extreme or more extreme than what we actually observe. And if it's a two-tailed test, well, we multiply it by 2. All right, now, this holds true if our data are random and independent, which they normally will be, or I'll tell you that they are in this class, and our sample is normally distributed. If our sample is normally distributed, then this transformation, this equation, will follow a t-distribution, and we use the t-distribution to then calculate our p-value. But if we're not normally distributed, then this won't hold. This no longer follows the t-distribution, so if we use a t-distribution to get our p-values, we'll have the incorrect p-value. So how do we check it? QQ plot. Check normality first. All right. So how do we do it in R? Well, it's a little bit different. So we could do it by hand and use the PT function to get the error, to get the values. However, if you have a sample, well, then you have all the data points that you need. Take those data points, get them into R as a vector, and then use the function t.test. T.test, you pass it to your vector, you specify mu, what your hypothesized value is, so mu equals some value, and then you say, is it a two-sided test? Are we testing if our value is less than that mu? Are we testing is it greater than that mu? And let R do all of the conversions and calculating the p-value for you. What happens if we're non-normal? Well, some people would say you can use a non-parametric test. And the one that they often suggest is something called the sign test. Or they could say like a Wilcoxon test. Assigned rank test. The problem with those is that we're actually testing the median at that point. All right, so it's not, if you're really interested in the mean, a sign test isn't gonna work. But occasionally though, you are saying, you know what, we're already skewed. Median's a better measure of central tendency, and that's what I want to measure. In which case, yeah, let's run the sign test. So the sign test is actually testing if our median, our sample median, is equal to some hypothesized value. It's not the mean. All right. The sign test works by converting our values into pluses and minuses. So is our values greater or less than? Is each of our values greater than or less than our mean? And it's coded as a plus or a minus, or a 1 or a 0. And that's a dichotomous variable. Right? I should say it's a plus or a negative, because if it's actually equal to, that gets keyed as a 0 and it drops out of our calculations, or sample size gets dropped out. So once we have this dichotomous variable, it's like flipping heads and tails. If our value, if our median is equal to that hypothesized value, then we should have an equal probability of being above and being below. So we're going to see, based on our sample sizes, did this probability of being greater, is that equal to 0.5? And that's a binomial test. And we'll learn more about a binomial test with our categorical data. You know, for now, I'll have a script for you to run this test. So our assumptions, data are random and independent. Again, this is going to be, I'm going to tell you, just make that assumption for this class. Second thing is that we need more than 5 data points. Those of you saying, oh, I'm just going to have a sample of 3 or a sample of 4, it's not good. All right. In order for this, we need more than 5, because if we don't, then there's no possible way to get a p-value less than 0.05. If you don't believe me, try it out. Flip a coin 5 times. Do it over and over again, and always check, is that coin fair? Or do we have an equal probability of flipping heads or tails? You will never get a p-value less than 0.05. It's impossible. Right? It's just how it works. But if you have 6 flips, now you can't. You have to do 0 heads or all 6 heads in order to suggest that the coin is not fair. All right. Hypotheses for this test: median is equal to some predicted value, or the median is not equal to some predicted value or some direction. All right. And then I present the binomial test here just for completion. We will get to this, but it's saying that the probability of being greater than the mean or less than the mean is equal to 1/2. And that's kind of what we're ultimately getting at. The sign test makes our conversion so that we can then run our binomial test. That's how it works. How do we do it? Here's our script. And I posted this. All right. So we run it, and then sign.test becomes available. Then we do sign.test. We give it our vector x, numeric vector. We specify our median, our hypothesized median. You use alternative. It's kind of set up the same way as a one sample t-test. We give it our vector, we give it our hypothesized median, and then alternative equals, two-sided, less or greater. All right, for both the t-test and this sign test, the default is two-sided, because that's typically the most common test that we run. We don't go in with a preconceived notion that it's going to be greater than some value or less than some value. So how do we do it? What is this doing? Just kind of quickly stepping through it. First, we pull out all of our missing data points. All right, so we NA omit our vector. All right. NA omit any values, and then we calculate the median of our vector. All right. We don't really use it. That's going to come up in our results section. We pull our hypothesized value. This is the value that we're looking at. And then we run a logical. We go row by row and record, is our vector greater than that hypothesized value? Is our value in that row greater than our hypothesized median value? If it is, it's keyed as a 1. If it's not, it's keyed as a 0. We do that row by row, and we sum it up, and that tells us how many positives we have, how many values exceed that median. We then do the same thing with the less than sign, so we need to know how many values are less than that. Now we can't just do total sample size minus our positive, because I said, if our values equal the median, they don't get counted. They get keyed in as a 0, so they get lost from our analysis. So we need the number of positives, we need the number of negatives, we have our total number of samples, so now the POS over the total represents the proportion of our values that exceed the median. Now we're setting up what our test statistic is. Is it two-sided or greater or less and so forth? And this next line tells us which value are we taking. So basically, are we going to use the positive or the negative value? And I have to do that in order to make that less or greater than work. Right? That less or greater than work. That's kind of hidden in the background. And then here's our binomial.test. As I said, the binomial test. That's what we're running, where we're testing if the probability of success is actually equal to 0.5. So we're comparing our actual observed, this is number of positives, compared to the total number. Is that proportion equal to 0.5, yes or no? And we're getting our p-value from that, and then the rest is just the output. So when we run it, it'll actually say, here's your observed median, here's the hypothesized value. You're running a two-sided test, or a greater test, or a lesser test, and then here's the p-value of that test. So I have it set up that it works properly. That is posted in the useful function script. That just a little bit. There we go. So what you can do is download it from R, open it up, copy it, paste it back into your useful functions so it's available. All right, randomization test. This is the last, and we're not doing repeated practice because this is stuff that I've covered in the undergrad stats course, and we've got abundant videos and PowerPoint presentations and so forth. All right, so randomization test. We're going to use bootstrapping. Bootstrapping is simply resampling with replacement. We've already seen it. All right, bootstrap 95% confidence interval, definitely easier to calculate than the bootstrap t-test, and we already have the function. All right, so you already have this function. It's going to generate a confidence interval of the mean. We could rewrite it again. We can rewrite it if you wanted confidence interval of the median. So if you were interested in the median, we could rewrite it to do this. And this works. This works. There it is. All right, so how do we interpret it? So here's some example code. So everyone kind of gets the same value. The same confidence. So go ahead and run these functions. This little caret is the line that was run in R. So after you copy and paste it into your markdown, you're going to have to delete that caret, or you can just type it out, set seed, 1 var, bs.mean, and so forth. And don't forget, if you run the bs.mean and it says function not found, you have to run that function script first to get bs.mean in memory. So we run it. What's the purpose of the set.seed function? We all get the same numbers, and it's very important. Once you run that set seed, any randomization test has to proceed in that order. You can't like run set seed, do the do the one bar, do the one bar again, and then run the bs.mean function because you'll get a different values. So it's meant to run one after the other. What's this one bar function doing? How many values? So you're right. Okay, so we're drawing a random sample from a normal distribution, saving it as the variable one bar. How many samples are we drawing? 2,000. 2,000 random samples from a normal distribution. That normal distribution is defined by its mean and the standard deviation, so we're drawing it from a mean of 25, standard deviation of 3. All right, and then we run the bs.mean function, get bootstrap confidence interval, and these are the numbers that we should get. All right, so that doesn't answer the question of is our mean equal to some value? All right, so how do we interpret this? Well, we look at this value and we say, if our hypothesized value is captured by this interval, then we conclude that our sample mean is equal to that hypothesized mean. So our sample mean is going to be equal to any value hypothesized to be between 24.8 and 25.06358 or whatever. All right, it's supposed to be exact, but 24.80000 all the way is just slightly outside that. But then where's our rounding, right? So let's just hope you're not right at that edge. Let's just hope we're not at that edge. Which means then our sample mean is not equal to any value outside of this range. So if we say, is our sample mean equal to 23? And we know we're working with non-normal data. And we get a bootstrap value like this, well, 23 is not captured by that range. 23 is all the way down here. So we would conclude then that our sample mean is not equal to 23. If our hypothesized mean is 26, well, 26 is way up here. It's not captured by the mean, so we would conclude that our sample mean is not equal to 26. That's our interpretation. The problem with this is that there's no p-value associated with it, and some people can have problems. But if we do a bootstrap t-test, which is a little bit more intense, and it will generate a p-value, we get the exact same conclusion. We would make the exact same conclusion. All right? Just like if we had a normal variable, our data actually meets the assumption of a t-test. If we use this instead of a t-test, yeah, we'll get the same conclusion. Our bootstrap confidence intervals would capture our hypothesized mean when our p-values are greater than 0.05. If our p-value of that t-test is less than 0.05, then our bootstrap means would not capture that hypothesized value. That's how it works. All right? All right. Practice. Scoville.csv. Going to have you write the results as if you're reporting them in a manuscript. You're going to do it here. All right, so you can kind of review, check your answers, give you practice. All right, so question 1. You found 2 unmarked vials with the Scoville label on. You don't know where they came from. You just found them. Maybe your advisor went in and messed around with it. Maybe another grad student, or my personal favorite, an undergrad, went in and messed with your stuff and left 2 out. All right? So, vial 1 is marked Scoville equals 4950. Vial 2 is marked Scoville equals 4000. All right? We want to know, are these 2 vials part of our sample? All right, so for vial 1, I just asked, is it part of our sample? Vial 2, not only am I asking is it part of the sample, but is our Scoville that's measured, this Scoville equals 4000, is it less than our sample average? So you're going to do a z-test for that. All right, and you might ask, well, what's our population? Well, your population is the sample, is your collection of samples. All right, that's your population that you're working with. You just found an unknown sample here. All right, you just found your unknown sample. So you're going to run z-test for that. Question 2. Is the average number of peppers per plant equal to 37? If you're going to perform a t-test on that, make sure you check the assumptions before you run your t-test. All right. Then, you got question 3. Is the median thickness greater than 0.23? Go ahead and use the sign test to check that. All right, and again, no, you can't use the t-test because I didn't ask is the mean thickness. I said is the median thickness. That kind of changes what tests are available to us. So use the sign test for that. And then question 4, is mean thickness equal to 0.28? Utilize bootstrap 95% confidence intervals to answer that question. So go ahead and work on these. Make sure when you do your test, have a write-up. A sentence is all that's needed. Maybe 2 sentences if you're going to check your assumptions. But have your write-up. Make sure you include all of the items that you must include when writing up results of the statistical test. All right. So go ahead, work on this. I'm going to call it street. What's that?
Oh, I'm talking about that.
Yes, sir. My Polymer Studio. How's it going?
4.
What's wrong with it? So what's going on?
What is going on? That's a big question.
I haven't got.
I made a number. I made a number. You don't have, I think it's. What are the, what are
Oops.
I don't think that's right.
P-values are between 0 and 1. If you get a p-value much greater than 1 or outside of those bounds, check to make sure your lower dot tail is correct.
I have a question for you.
Because you might be doing the wrong tail and then you're getting more than 1.
That's what I did.
What's that?
I did both, man. I got one.
Go back and look at the z-test where I get the example of the function here.
Because the is larger.
So here, t-test, right? I say where x is a numeric vector.
Okay.
Now scroll up. Here, x is the test value. It's not a vector. So what you've basically done is kind of a z-test for every single value in your sample at this number.
So how do I get it?
That's what we're testing against.
Lower tail false.
Oh, it is false?
False. Because that, false is greater than, X is greater,
Okay, I got, so literally got 0.0.
Alright, let's get this z-test.
Yeah.
So my analysis didn't change.
No, you did it, you lined it up right, you said the wrong tail.
There you go.
So you've got to go to this. Told you what test to run. If it's a 2-tailed test, we do 2 times that. If it's a 1-tailed test, we don't. Alright? X is our test value. That's what we are testing against. This is what we observed. That is our one vial. Vial number 1 had 4950.
So we don't
That's
have
our
to
X.
put the Scoville data set in there at all. We just put 4,000.
Mean and standard
We
deviation.
got them.
That's our population. This is where we're getting from our actual data set because our data set is the population. So you're going to have to calculate the mean of the Scoville units, and then you're going to have to do the standard deviation. But remember, it's actually the standard error. We need this, the standard deviation divided by the square root of our sample size to go into here.
Either way.
And what's our sample size?
What that?
One. It's our one value. It's our one test statistic. And then the lower dot tail, as I said, you're going to know pretty quickly if you screw it up. Lower dot tail tells us which tail we're calculating probability of. If you use the wrong one, then you're not calculating the tail, you're calculating the rest. And when you multiply it by 2 then, you're going to get an odd value. Why is that? Total area underneath this curve is going to sum to 1, which means our p-value is going to be between 0 and 1. If you took this chunk from here all the way to negative infinity, and you multiply that by 2, we're going to get an area that is much larger than the area underneath this curve, which means our p-value ends up being greater than 1. You can't have that. It's not possible. So you look at our hypothesized value. Is this value less than this mean value? If yes, then yeah, then use lower dot tail equals t. We're going to look at that t because our test value is then less than our mu. But if our test value is greater than that mean, then we're going to have to use our f because we're working with our upper tail of that.
Okay.
So when I ran it, up. All right, so is this part of our population? I've set up our null hypothesis is x equals mu, where mu is our population. That is the mean of Scoville, $ Scoville, as I read it in Scoville. Our alternate is that our x is not equal to that mu because we said, is it part of the population? If it is, it's equal. If it's not, it's not equal. All right, and these are just the ways. So if when it knits, it gives the not equal sign. This gives the mu sign. So it's pretty cool. So then that first chunk, first thing I did was calculate the mean of that Scoville. Because I wanted to know, I needed to know what this value is, because that tells me if we're using lower dot tail equals t or f. All right. In this case, our test value, 4950, it's greater than that value. So we're at our upper tail. So it's a two-tailed test because that's what our alternate is. So 2 times p norm, 4950, that's our test value. The mean is equal to the mean of Scoville, $ Scoville. That's our population mean. Our standard deviation is Scoville, Scoville, divided by the square root of 1. How did I get the square root of 1? We have one sample. We've got one vial that we are working with. And then lower dot tail equals f, and I get a p-value of 0.09. Yep.
This is probably a dumb question. So then if we had like 2 samples, we get the square root of 2, 3 samples, square root of 3.
Yes. So when you have that, if you had 3 vials, so if I took both of these, they're unknowns, and we took the average, and we said the average Scoville unit is whatever. We can't calculate a variance or standard deviation of that because it's only 2 samples. In which case, yeah, you can take the average there, compare it to this, and then you would do square root over 2.
Okay. Thank you.
Get it?
I got the same answer, but without square rooting.
What happens if you take the square root of 1? What happens if you divide by 1? I like putting it in here because it emphasizes the need to do that. You actually do need to do that. So if we had a situation just like what was asked, as I said, we had a sample of 10 vials. Here's the average. Maybe I didn't give you the standard deviation. Now, how often are we going to do that? Not very. Most likely scenario for this is you catch one sample. You're driving down College Hills and you see a dead skunk on the side of the road. Run over. You look at it and it's like, man, I can't tell what species it is because you haven't had an analogy yet, right? All right. So you measure like a skull, and you said, okay, well, I know what the species averages are. Yeah, I know what the species standard deviation is. Is this measurement part of our population? Kind of answer, is this one species or the other? Again, how likely is it that you'll do this? Probably not. It's unlikely, quite frankly. Because normally what you have is a sample. This is how we do vial 1. Go ahead and do vial 2. Now that you see. Yep. Yeah, look at the code for T-test. On your presentation. What is X? What did you give it? Is 37 a vector? Pay attention to what we have to give it, vector or values.
Do you mind going back so I can take down the U sign again?
Oh, $, backslash, mu, $. Yep, I'll have it up. And that's if you need like beta or alpha, same general format.
Okay.
So it's another sign rotation.
Yeah, because R will use this to calculate the mean and standard error, but it then uses to calculate your t statistic. And it also uses that to figure out the degrees of freedom.
Okay. Yeah, I was messing that back. Yeah. I mean, it's what you It's just possible.
It's been 3 months.
It's been a little bit. Okay. Oh, my goodness.
The only thing we're changing is the true mortality.
Oh. Actually, I was speaking to Diana.
Listen.
Sorry, yes, if we're doing that.
Yeah.
Oh.
I didn't know the word page come until I heard you.
Good. Yeah, I was totally up and down. Or did I have to walk all the way into my house? Yeah, you walked over my house and got in there.
so I just had new dog with a. He's on Sunday, huh? Sunday.
No, Sunday's the 14th.
Oh.
The 14th is Sunday, 16th is Monday, 16th.
Not. When is that?
The 14th, Sunday.
I know what you did. It's like a bus thing. People with dinosaur that has dinosaur problem on it. And someone get it that, it has like, stop it.
Garrett, source like. That's what you do. I mean, why?
Higher than.
I mean,
For the,
I don't know how to do that.
type out, you just type
Is that just a normal thing?
you put those in
No,
like
but I
that.
have a hard time.
the first one is your
It
no.
doesn't.
Right, 37.
No. No, 37 is hypothetical, you're testing to see if the known value is the actual.
I think we did.
We did. Here.
But the other two, you equal. It was also the first.
I'm so sorry.
Well,
Use Microsoft.
I'm better than I am the cheating. Low bar, but I answer.
It's a low bar. So I'm there. I'm there for it. Where's that? So tired of that.
What is?
What's the error?
Oh. So.
True mean is not equal to 37.
Yeah, the p value, yeah, I got it.
Yeah.
I tried to do
Because that's meaning that value. Then, well, maybe.
So,
Use
X,
that. Yeah, I was getting that stuff.
X is the data that you pull straight from the data set.
Couldn't figure it out.
And then U is the. Testing to see if it's equal, so that your alternative. Two-sided semi quote.
What? It's very gratifying, like, I'm doing it.
Yeah. Typing.
Oh, dude, I tried
Downside everything.
Nice.
You don't, no, you already have.
Game changer.
What are the problems?
We're gonna wait.
He's called, so I have our own.
I can hear you.
So,
Did something wrong. Oh, yeah. Yeah, you did.
yeah, rather than typing out the actual number. it's still-
Yeah, you should probably.
You like, you want? What's the alternative?
Good. You recognize maybe one should have it.
I'm trying to check the terminology. Why don't you want?
No, you can do,
Use capital P.
well, I did, so, I did not, but
I know you're plugging in the code, like, I don't.
These are different.
No, so,
Yeah.
that's why it's nice to have.
Yes.
So then, so I have a lot of.
Yeah.
Oh,
All the way.
okay, I put that in there, two sides.
Yeah, okay, thank you.
That's good. All that for that.
When you get?
You know, Bethany, as long as you're on the side, you're okay.
And then, so which one do you use? Oh, I haven't done that.
Something like that.
Average number of pepper.
So that then you have that.
0.05.
Do what?
Yeah.
Yeah.
It says, the true mean is not equal to 30.
Oh, no.
So barely. One second. Oh, you're only. Yeah, that's what Yeah.
Yep. When I'm adding a new chunk, it's not.
Hey, what's the alternative?
Top right? You know what?
Did you add
What's
it?
the alternative? Is it R? Two sided equal?
Yeah. And like over here.
Yeah.
Yeah, that's right.
But.
Runs down here.
Yeah, but mine, but they
No, I haven't.
In the meter, just find a minute ago, I was going through it after that. For my T-test, they want to give it that. Give all those the
There,
R.
I do.
And you can have it. Yeah. I don't have like
That first layer.
this.
Yeah. That's what you type in. Yeah.
Yeah, that's the whole thing, you run that.
Yes, where's the next part? What do I type in? Where is this part?
So your X, so your X, yeah. So your X is
Median is
Save and then like reopen our studio. That might
I think so,
help.
right?
Do you need
Yeah.
to?
No. Yeah. And then if it was outside of that.
It's graded.
Oh, because that would just be, I'm not sure. Like, in general.
For alternative.
Question 3?
If it's graded on. It's two-sided on, like question 4 would be two-sided, because it's just saying if it's.
Yeah.
Like both sides.
It's hard.
Like,
Assignments. I was talking out loud. X is two numeric factors. So it's not a set value.
When do I know which X is which?
Yeah.
I'm tired of not knowing which.
look at the function. When I give you the example, I tell you if it's a value or a vector. The vector, you're probably going to have to pass a data $sign variable.
Okay.
Where do you
Write these things down. For the, I'm on DS.
Yeah.
It doesn't matter.
So I've got the Z test and I've got the T test. So like your P norm, X is a test value. The T test, X is a numeric vector. I didn't give you the sign test, but X is a vector. That's what I should have given the example. And then bs.mean goes back to an earlier presentation where X is our numeric vector. It is. Most of the time it's going to be a vector. Most of the time it's going to be a vector.
So on part 2, biochemistry, that was a one-tailed test, right? So X was asking if it was less than. So it's just the P norm, not two tests.
Are we gonna go with a little $sign, whatever, on all of them? Is that right?
The Z test should have just been.
Z test is just a value.
Your one value?
Okay.
You got it. Oh, no, I didn't, yeah.
Yeah, no, you did, right? You
I did,
did,
right?
you did the single thing on the.
Yeah.
Yeah, X was the X.
Yeah, I would say yes.
No, I got an answer. Yeah.
So we should be able to go through
The write-up.
and do some practice while it's fresh. How's it going?
Oh, I was wrong.
Well, oh, you are now expiring, right? There we go. That's good. Okay. Yeah. What's your last week? shit. I put this in my pocket. I gotta pull that.
Yeah, I shouldn't wear black. This school is like that white cap. Just gray pants. And then they all have wonders.
This is in reference to our alternate hypothesis. We are testing how likely are we to get that value equal to that
Yeah.
if they are equal. We said no, it's so we reject our null hypothesis that they equal, and then conclude it's greater.
Yeah, I was gonna say, I usually move them both.
All right. Let's review this. Just bootstrapping. We've done bootstrap confidence intervals last week.
Yay.
So I got question 1, 2 vials. We already did. First one, 4950. All right, walked it through. So vial 2 had Scoville unit marked as 4,000, and I asked, is this less than our sample, or is this less than our population? All right, so our null hypothesis is that 4,000 is equal to our mean, which was 4517. Our alternate is that our sample, that 4,000, is less than the mean value of the population. So this is a one-sided test. So we don't multiply it by 2. We just use p norm, our test value, which is 4,000. That's our single vial. All right. The mean, we're comparing it to a population mean of whatever our vials are. So 4517. Standard deviation of that divided by the square root of our one vial. Lower dot tail is equal to t because 4,000 is less than this. So we're looking at our lower tail. How likely is it to get 4,000 or less Scoville if we actually have a mean of 4517? Well, it comes up with p-value 2%. 2% chance. That's too small for us to conclude that our sample is part of the population, so we reject our null hypothesis. And we conditionally accept our alternate, which says, yeah, our vial does appear to be less than our mean, less than that population. All right, so question 2. Mean number of peppers equal to 37. So our null hypothesis, mean is equal to mu, right? Where our mu here is 37. Our alternate is that the mean is not equal to mu. That's our alternate. All right? So we want to run a t-test. First thing we do, check our normality. Yeah, it looks pretty good. Just 2 points, those are at the extreme, perfectly fine. Perfectly fine. We then run our t-test, and I get this. All right, here's our output, gives us our test statistic. Negative 1.91. Our degrees of freedom, 199. Our p-value, 0.05711. All right, our alternative, it says it's not equal. That should correspond to what our alternate hypothesis is, that it's not equal. It gives us confidence interval, 95% confidence interval. This is a parametric confidence interval. And it gives us our sample mean. So using that, we look at our p-value. Is it less than 0.05? No. It's greater, slightly greater than 0.05. So we fail to reject our null hypothesis. We assume that our sample mean is equal to 37. So in my write-up, mean number of pepper plants
is equal to 37. It's my conclusion interpretation. Test that we ran was the t-test. Our test statistic, 1.91. I know it was negative, but t-distribution is symmetric around 0, so it's pretty much convention if you're going to do two-tailed test, just to report the positive value of that. We have degrees of freedom, which is 199, and a p-value. In this case, I did less than 0.06, because it would round to 0.06, not quite 0.06, but it's greater than 0.05. All right? Now, how did I get my degrees of freedom? This is one way to list it. All right? And this is an R. So hopefully, if it renders properly, so I know if I rendered this as a PDF on my computer, this will actually be T and then a subscript 199. I don't know if Word will render this as a subscript or not. But for the class and the markdown documents and the write-ups, you can use the underscore or just put it in bracket. Put your degrees of freedom in brackets because that would represent our subscript. If you didn't want to do it that way, then you would do T equals 1.91, comma, DF equals 199, comma, and then P value. All right, that's our t-test. So again, our null is that x is equal to mu. We failed to reject that. Question 3. So median thickness, we asked, is it equal to 0.23? And actually, it didn't ask if it's equal. Is our median thickness greater than 0.23? So it goes to our null hypothesis, always. Our sample belongs to the population, which means our medians are going to be equal. That's always going to be our null hypothesis. Our alternate in this case, we specified direction. So our median is greater than the hypothesized value. I already ran my function, so sign.test is available to us. So sign.test, Scoville $thickness, median equals 0.23, alternative equals greater, and it runs out with a pretty decent output, I might say. So it tells us what we ran, told us our data, the observed median. So our median in the data set is 0.256. The observed, our hypothesized median is 0.23. That's what we're testing against. We're asking, is this value greater than that? Yes or no? With a p-value of less than 0.05, we know, yeah, it is greater than. Why is that? Well, less than 0.05, we reject our null hypothesis. It's too unlikely that we would get this value or larger if our medians were actually equal. So we reject this claim and conclude, yeah, our median's greater than 0.23. My write-up, conclusion interpretation, the test, sign test, and then the p-value. There's no test statistic, there's no degrees of freedom associated with this. Right. Then our finals, just bootstrapping. So I did, since I've been doing it for the rest, just kind of emphasize our null hypothesis is that our sample mean is equal to the mu, whatever we're hypothesizing. All right. Our alternative is that it's not equal, so we didn't set direction. You could, all right, but that's not really going to affect your. I guess you could change your confidence intervals a bit, like where you're going, but generally for this, it's are they equal or are they not equal? So I use 10,000 iterations. I get this interval. This interval did capture 0.28. So for the reporting, this is one of those situations where we don't really have a test. We don't have a p-value. So, but we do have confidence intervals. So you're going to have to report those someplace. You're going to have to specify that they are bootstrap confidence intervals. And then your iterations typically would have been stated in the methods. So if you're going to use bootstrap confidence intervals to make some of these comparisons, you're going to probably specify that in your methods section. You're going to say, I'm going to use 10,000 iterations to generate these confidence intervals. All right. If that didn't specify, if you didn't state that, then you would have to say, mean skin thickness was compared using bootstrap confidence intervals with 10,000 iterations or something like that. All right. But in this case, yeah, our confidence interval captures 0.28, so our mean skin thickness does appear to have a mean value of 0.28. All right, questions? Last bit. Homework. Released it. One continuous variable test review. All right. So we've got a RMD file, we have continuous var, and we have a Word template to docx. All right. What you're going to need to do is download the files. You're going to have your markdown, this RMD file in a folder. You're going to save this Word template, and you're going to put it where you are working with that template file. All right. So for us, I think it's here. I already have it in my folder, so I'm not going to resave it. And you need that because wherever we saved, when we're done, you're going to have all your answers. And you go up here to knit, and we're going to knit it to Word. All right, so no, it's already saved. And then, there it is. Yours might pop up and show progress, but if it works, then we will get a Word document utilizing the styles that I put together. So this has everything that I've been working on in this class, including the stuff that's probably most fresh, which are this homework. All right, so you can see that all the printouts, you can see the equals, less than signs, and so forth. All worked. Not equal sign worked. That didn't work. Not sure why that didn't work. Something happened. But this is what you would get. You would then export it as a PDF, and you would upload it. I'm going to ask that you have this done by class on Wednesday. That makes you do it. If you run into problems, bring your questions to class. All right? It's definitely something kind of repeating and everything that we're learning with the tests. So if you run into problems, even if you run into problems knitting, bring that to class. I'll work with you. We'll try to get it set. All right. All right. We're done.